Okay, so I filmed this yesterday and I went to edit it and I lost the introduction for whatever reason. So I'm going to go back, do the introduction, and then the vocabulary, and after we get through the vocabulary, it'll cut and go into what I filmed yesterday into the concepts. But we're going to have three major concepts: angles inside and on a circle, tangent theorems, and then angles outside of a circle. And I might change the order later when editing this together. I might put angles in and on next to angles outside, and then tangent theorems. But then inside of each of those concepts, there's going to be some other minor concepts. But first, we have to get through the vocabulary. We have just four definitions here. Chord, diameter, secant line, and tangent line are different kinds of lines in a circle. All right, so a chord is a line or a segment with both endpoints on the circle. And what that would look like here is if we have our circle, a chord would be, something like this, where we have a segment here, and both of the endpoints are on the circle, like this, as opposed to in the circle or outside of the circle. Right? Just on the circle, like that. Then a diameter, you know what a diameter is, but the technical definition of a diameter, is the longest possible chord in a circle, and it must pass through the center. And again, a diameter. If you have your circle, it goes from it has both endpoints on the circle, and it goes and passes through the center of the circle and has another endpoint like that. And again, like that. And, something like if we were told, we'll call this line A, B, C. If we're told that point B is the midpoint of line AC and line AC is a diameter of circle B, then we would know point B is the center of circle B. Like that, because it always has to pass through the center. And then tangent and secant lines. I don't know if it's a J, it's a G, I'm sure. And Gent line. A tangent line is a line or segment or ray, just some kind of line that contacts the circle at one point. So what that would look like is if you have your circle, a tangent line to this might be, something like that, where it only touches right there and it goes on. Or, something like this, where it touches right there and then it keeps going, as opposed to, going through it like that. And then finally, the secant line. And these lines are named after trigonometric functions. And I'm not going to get into, why. But the tangent we already talked about, the secant is the opposite of the sine, right? Remember the sine was opposite over is the opposite over the adjacent. I apologize. I don't know what I was thinking. I had a brain fart there. The sine is the opposite over the adjacent, so the secant would be the adjacent over the opposite. But you don't need to know that until trigonometry or pre-calculus. But if we look here, we have the secant line. The secant line is a line passes through a circle. So what that looks like is like the opposite of a tangent line. I apologize. And contacts at 2 points. So what that looks like is like that, where it goes through and it touches it twice right there. It goes through and it touches it twice right there. And this is like, back in algebra when you had when you were doing domain and range, where you would take, like if you were doing the domain, you would take your line and pass it across like this. The tangent would be where you come and you touch it once, and then the secant is as you go through, and then the tangent is where you touch it once again, right? And so if it's secant, then it's not a function, and if it's tangent, it is a function, is what the domain would be, right? Back in algebra, if it touches it once, it's tangent, then it's a function, not a function as it's a secant, and then tangent again, and function again. And then with that, you'll go off to the next into central angles and inscribed angles of a circle. Okay, nope, this is me again. Less than 5 minutes later, I only went over the inscribed angles. I forgot to go over central angles here. So I'll start with central angles. What is a central angle? So a central angle, is an angle with its an angle with its vertice at the center of a circle. Hence the name central angle. So what this would look like here is if we have our circle, and our center is like here-ish. This angle, its vertice would be here, and then it would come out like this. So it meets in the center of the circle, and then it comes out to the edge of the circle, right? So, or something like this. This angle here, it meets at the center, then it comes out. That'd be like 170 degrees, 165 degrees, like that. Whereas an inscribed angle, is an angle with its vertice on the circle. Right, so it has its vertice on the circle rather than in the circle. So what that would look like, if the center is there, this would be an angle like that, right? Where its vertice, it meets right there on the circle, and then it goes off to the rest of the circle, like that. And then now I'll get into the angle relationships, right? So I did this kind of backwards, but that's all right. If we have our central angle here, like this, and I tell you this is a 70-degree angle, and I want you to find this arc angle right here between these 2 points, how would you find that angle? Well, that angle is going to be the exact same measure as the central angle to its points, so this is also going to be 70 degrees. Right, same thing, if we have one here like this, and I say this is 90 degrees, then this arc right here is 90 degrees. Right? So the arc angle is always going to be the same as the central angle. And now, hopefully, I don't have to cut back in today to this video, and we should be able to pick up where we left off. Hey, sorry about that. I think we left off on the inscribed angle, and an inscribed angle, like this, if we say this is, x, this is going to be 2x, right? So this is always going to be twice the length of this. So, for example, if we have here 40 degrees, well, this is going to be twice 40, so this is 80 degrees. And vice versa. If I'm told that that is 80 degrees, I can take half of it and know that this is 40 degrees, like that. And now I have 6 examples, and then we'll go to tangent theorems. I've got to put some Expo spray on this board. If we start at 3 easy ones, 2 moderate, and then 1 difficult, we'll start here like this. And I want you to find this arc length here. Well, you know that this is 90, it's a right angle, this is 90, and this is the same, so this is also 90, like that. If we have another one here, a circle, like this, I tell you that this is 80 degrees. And I ask for this length here, this arc length. You know that this is, or not the length, but the angle. You know it's going to be twice this angle, so it's going to be 160 degrees, like that. And then what if we had instead here, we know that this is 90 degrees. So what is this angle right here? Again, it's going to be half of this, so 45 degrees, like that. Okay, now I have a bit more difficult, but still, doable. If we have a circle in the center, like that, and then we make some weird quadrilateral. That's not supposed to be curved, I just messed it up. Kind of like that. And I tell you that this arc angle is 100 degrees, and I ask you to find this one and this one. Well, first, this is a central angle, so it's going to be the same as this. So we know that this is also 100 degrees. And then this here is just half of this. So this is 50 degrees, like that. One more like that. So if we have this, here, and I tell you that this is 40 degrees, like that, and I ask you to find this and this arc length or arc angle. Well, first you have to take this and double it to get this length. So 40 times 2 is 80, and then this here, 40. Well, then we don't even have to use 40. We just know that these are going to be the same angle, so we know that this is 80, like that. Now we have one more. Here we have a circle like this, and we have something like that, and I tell you this is 20 degrees and this is 30 degrees. This is the center, and I want you to find this arc length and this arc length, as well as this angle, this angle, this angle, and this angle here. So if you want to pause, write that down, try to figure it out. Okay, so first we're going to start with these two inscribed angles. We see the 30 degrees and the 20 degrees. Well, this, if we ignore this here and this line here, we see that we have just a normal inscribed angle, which makes this twice this length, or 60, like that. And then this one down here, same thing. If you ignore this and this, you get this up here is twice this, or 40, like that. And now we can figure out this angle and this angle, right? So this is another inscribed angle that touches the 60. And same thing here, another inscribed angle for the 40. Right? So if we just take half of this to get this, right? Half of 60 is 30. Not 300, that like that, 30 degrees. And then same thing here, this goes to this, and it makes it 20 degrees because you just take half like that. And now you know a triangle adds to 180 degrees, right? So so first we have to add these together and get 50, and then we just take 180 minus 50, which gives us 130, right? So we know that this is 130, and then up here we know that these two angles are vertical angles, so that this is 130 as well. And you know what, just for gits and shiggles, we can find this length and this length as well, right? Because this is a central angle, and this is a central angle, we can just add them together and we can just bring them in, and we get these 60 degrees and 40 degrees like that. You know, we can even find this arc length and this arc length as well, because we have another central angle at the 30 degrees, so we can just bring that down and make this one 30 degrees, and this one up here, 130 degrees, like that. So there you go. We found every single angle on this diagram given just two angles from it. And with that, we'll go to next the tangent theorems. And we have 3 tangent theorems, I believe. Yeah. 3 tangent theorems from there. So first is the tangent and intersected chord theorem. So this is, and I'm not going to write all this out because it would add 3 minutes to the video, so you can just, write it out as I say it. This is the angle formed between a chord and one of the tangent lines at either point of the chord, right? So the tangent line that intersects at the same point as that chord touches the circle, and there will be 2 tangent lines for each chord, right, at either endpoints, and is half the length of the arc length it is on, right? So what that means is if we have our circle here, and we have, a chord like this, and we'll put our center about there. We have a chord like this, and a tangent line right there at the same point that chord touches the circle, like that, and we'll label this A, B, C, and that B is just like on the circle. It doesn't mean anything except for when we're labeling the arc later. So we know, and it says the tangent line at either endpoint is half of the length of the arc length of the arc it's on. Right, so what that means is if we label this, angle X degrees and Y degrees, we can say that angle X is equal to 1/2 of arc AC, right? So this angle right here between the tangent line and the chord is half the length of this smaller arc made. And we can also say the angle Y is 1/2 the length of arc ABC, like that. So, and then again between the chord and the tangent, not between the chord and the circle, because, if we go between the chord and the circle, I mean, this is going to change the farther out you go. So it's between the chord and the tangent. That angle is always going to be half of this big angle here, like that. So I read to you the technical mathematic definition. You can write it however you want if you're taking notes. And I'll give you just a few examples to work through. Number one, we have a circle like this, right here. Our chord and tangent, like that. We'll label this A, B, C, like that. And I'll tell you that ABC is 220. And I want you to find angle CAE, so this angle here, and I want you to find arc AC, so this arc length there, like that. So if you want to pause, try it on your own, and then I'll tell you. Well, first we know that this is going to be half of this. So what is half of 220? That is 110, like that. And we know that these are going to be supplementary angles, right? So they add to 180. So we know that this is going to be 70 degrees, like that. And now I know that this is going to be twice the length of this, because you just flip it around. So if this is half of this, then this, or if this is half of this, then this is twice this. And then this is 140 degrees. So we can say out here that angle CAB, angle C, yeah, we can just say angle A equals, so this angle here equals 110 degrees, and then this angle here equals, and then this arc length, so we can say arc AC is 140 degrees, like that. And that would be your answer. For that, I think we have one more of these, and then we'll move on to the next tangent theorem. So if we have this circle, hopefully you're getting tired of circles by now, because you've still got like 7 more pages of them. And we have a chord right here, and a tangent line like this. And we say, we'll call it D, A, E, DAE, B, C, like that. And I will tell you that this right here is 140 degrees, like that. And I want you to find arc ACB. So I want you to find this arc here. And I want you to find this arc here, so this small arc, AB. And I want you to find ABE, angle. Angle A, B, E. That should be BEA, but we want to find A, C, B. We want to find AB. And we want to find angle BAE. Like that. So see if you can do it on your own. Okay, first we're going to find this. We know that this is going to be twice this. So what is 2 times 140? That's 280. So we know this is 280, right? So 280 degrees. Next we want to find this right here. Well, this is just going to be, these are supplementary. So we can do 180 minus 140, or 300, 180 minus 140. And we get 40 degrees for that one. And you can put that here as 40 degrees. And then this entire arc right here, AB, is going to be twice that, or 80 degrees. 80 degrees, like that. And that is the tangent, the chord tangent theorem. Like that. We have 2 more tangent theorems, and then we have something else. I don't know. I think I know. I made the material. Now I know what it is. I just don't know the order I put it in. Okay. The 2 tangents theorem. So I kind of talked about this at the beginning of the video. So the 2 tangents theorem says that if we have a circle, call it T, and we have 2 tangents that come off. Let me fix this circle a bit. So we have 2 tangents that come off like this, but they stop at the point where they touch the circle, like that. So they're just like tangent segments, but if they continued off, they would be tangent lines. And what we know from this is that these 2 lines are going to be congruent. We know that if we label this A, C, B, we know that AC is congruent to A, B. But let's prove that for a second, so that I'm not just telling you that they're congruent, so that you know they're congruent, and then you can never think about them being congruent again and just know that they're congruent, which I think is the proper way to do math, but you can disagree. Okay. So the way to prove this is with a circle here, like this, and our center, and our 2 tangents that go off, like this. And they meet here, here, like this. And I say this is L, K, J, M. And if we set up our 2-column proof here, statement and reason, like that. And what we're trying to do here is really prove 2 triangles are congruent, and then use that 5-letter acronym corresponding parts of congruent triangles are congruent to prove that these two lines are congruent. But first, if we turn these into triangles, like this here, and we're trying to prove that these two triangles are congruent. Well, first we can say that LM equals LK, or is congruent to LK. LM is congruent to LK because they are both radii. RADII. They're both radii of the circle. They go from the center to the edge. So we can put a dash mark there proving that those are congruent. Next, we can say that LJ is congruent to LJ. Because of the reflexive property. We can also say that angle LKJ is congruent to LMJ. We can say angle LKJ, or not line, sorry, is congruent to LMJ. And that these both equal 90 degrees because of a theorem that I haven't taught you yet, and that's a whole nother can of worms, and this video is already an hour long and I don't want to open it. But because of the tangent radii theorem, the tangent radii theorem. So we know that these are going to be 90 degrees here. And now we have three parts. We have, oh, sorry, I didn't put marks there. We have two edges and this is going to be, I'm sorry, this is going to be hypotenuse leg. We prove that the, hypotenuse leg congruency, because we have here the hypotenuse opposite the right angle, and we have a leg. So we can say triangle LJM is congruent to triangle LKJ because of hypotenuse leg congruency. And then from there we can say, because corresponding parts of congruent triangles are congruent, something I taught you back in chapter 2, I believe, CPCTC, we can say that MJ is congruent to KJ. MJ is congruent to KJ because of corresponding parts of congruent triangles are congruent. CPCTC, and we know that these are congruent. And now that we've proved that, I'm going to give you like 2 practice problems because we've already spent enough time proving that it's true. So let me erase all of this. Here, I've really got to clean my eraser. It's getting gross. Okay? Yeah, I have 4 problems here. I'm going to give you 2. I'll give you an easy one and a hard one. If we have a circle, center labeled P, and it goes off like this and like this, and we say this is worth 12, and I ask you I'm not even going to write all that out. What is the length of BC? Well, this is just going to be 12 because we just proved that those two are congruent. And now, give you the hard one I had planned. Here we have our circle, and we have a tangent line coming out like this. Well, that's not tangent. Like this. And I tell you, this is worth 3x squared minus 10, and this is worth 17. I want you to solve for x here. Well, first you go, we can set these equal to each other because we just proved that they're congruent. So we can say 3x squared minus 10 equals 17. We bring the 17 over 3x squared minus 27 equals 0. And if you solve the quadratic, I'm not going to do here because you already know how to solve the quadratic. We get x equals plus or minus 3, or plus and minus 3. But if it asked you for the length of this, you would just use, it's asking for x, not the length, so we get x equals plus and minus 3. Okay, we have one more tangent theorem, and then one more section, I believe. This one had sections in sections in sections. Yeah. Okay. When two chords intersect inside of a circle, the measure of each angle is half the sum of the arcs. Okay, yep. So this one isn't a tangent theorem, but it's a chords theorem. Okay. Hey, sorry, I'm trying to get this camera adjusted. When I press the button, it quit lining up. Okay, that should be good. Sorry about the cut there. I'd been filming for 2.5 hours. Well, not filming, but up here doing the math for 2.5 hours. And I took a break, but I'm back. We're doing the chords theorem, which states, and again, I'm not going to write all this out, but you can just copy as I read. When two chords of a circle intersect inside of the circle, the measure of each angle is 1/2 of the sum of the arcs, or of the arcs intercepted by the vertical angle. So what that means is if we have here a circle like this, and we have two chords of our circle, we'll have one here and one here like that, and they intersect right there, and we'll say this is A, B, C, and D like that. So what this says is if we have angle X here and angle Y, well, I can just use red again, and angle Y here in degrees, X degrees, Y degrees, right? If we want to solve for X, for the angle X is equal to, it's going to be 1/2, so x equals 1/2 of the measure of arc AD, well actually 1/2 the measure of arc arc BC, so that arc that it's on, plus the measure of arc AC. So the vertical angle of x right here, this is also x, remember, and then we want to take this arc right here, AD, like that. And this m means we're taking the actual length rather than the angle, right? Sorry, I'm looking to make sure you can see that whole board. Yeah. And then same thing for y here. The measure of alpha or y, I have y on there, alpha on here, is going to be 1/2 the measure of AB, right? This arc right here that touches it. So the measure of AB, sorry, these up here should be arcs, not lines, plus, and then it's vertical, which is also y, and then that is DC, plus DC measure, like that. So that's how you would determine the, these angles here. So let me give you a couple examples of this. First, we'll have our circle, and then here's our lines. There's one, and there's one. They meet right there. And I'll call this x degrees, like that. And we'll say this is 156 degrees. And this is 130 degrees, like that. And we want to solve for x, right? So let me write out here. A, B, C, and D, like that. Well, x is going to be the two vertical arcs added together, half of the two vertical arcs added together. So the two vertical arcs would be 156 and 130. So we would do 1/2 of 156 plus 130, right? So this goes to 1/2 of 186. Half of 186 is 143. I didn't have to look at the book for that. I knew that. 140. It's not 143. What am I talking about? Yeah. This here, I apologize. This goes to 286 and this goes to 143. I apologize. I made a mistake there. X equals, X equals, X equals, and that's your answer. X is 143 degrees, like that. I have one more example for you. Yeah, and then we have, okay, I don't know. I'll get there in a second, but we have one more of these, because this is pretty easy. I mean, you can, and if you want more practice, there's websites and stuff that have tests and practice problems, and YouTube has some good study stuff and that kind of thing. I'm just trying to get the concept down for you. Again, so if we have a circle like this, and we go here like that, those are our two chords. A, B, C, and D. And they meet right here, like that. And I'm told that this is 94 degrees right here. And you want to find the arc length of AB. We'll call it X degrees. Not the arc length, but rather the arc angle. I apologize. So if you want to pause, try to figure that out. How do you find X here? Okay, so first we want to find this angle right here. Well, we know that this angle is going to be supplementary to this angle. So we can do, 180 minus our 94. That gives us 86, right? So 86 degrees. And then from there, we can go, we can do this in reverse, right? So we can say, well, actually, first we also want to find, I apologize, I forgot to give one other piece of information. I didn't see it on there. This is 80 degrees right here. This arc angle is 80 degrees. Now from here, we can set this up again, where this right here is our angle. So we go 86 degrees equals 1/2 of this 80 plus X, like that. And then here we can solve this. We get 86 equals, we should probably multiply by 2 to cancel that out. We get from there 86 times 2 would be 80 times 2 is 160, 172. 172 equals 80 plus X, right? We subtract 80 and you get 92. 92 equals X, like that. And that would be your answer, right? This is going to be, instead of X, 92 degrees, like that. And that's your answer for this one. I think we have one more tangent theorem or something, and then we're done. So let's see. All right, hey, sorry I cut there for a second so that I could draw out this diagram, because I figured you didn't want to sit there in silence while I drew this out. From here, we've talked about the angles inside of a circle. We've talked about the angles on a circle. Now we just have to talk about the angles outside of a circle. And for an angle to be outside of a circle while still dealing with the circle, there are 3 ways you could do that. You could have 2 secant lines. You could have a secant and a tangent, right? There's your secant, there's your tangent. Or you could have 2 tangents, right? And now, if we're trying to solve for angle A, this outside angle there, on all 3 diagrams, we're going to use the same formula, like the same concept, but it's going to be written differently just because I had to put different letters, right? So you're always going to take, of the part of the circle that's inside your 2 lines, you want to take the bigger part minus the smaller part. Here, the bigger part minus the smaller part, bigger part minus the smaller part, right? So, like for this one, if we want to solve for angle A, we would say angle A equals 1/2 of our bigger part, which is DE. So the measure of DE minus the measure of our smaller part, BC. I don't know why I have a parenthesis there. Like that. So that's your example for two secants, right? If we have our secant and tangent, again, our bigger part is going to be the DC and our smaller part is BC. So we can say the measure of angle A equals 1/2 the bigger part, DC, minus the smaller part, BC. And then same thing here. So we're going to do the measure of, oh, I should put M's here for measure. The measure of angle A equals 1/2 our bigger part, EFD. And you don't just say ED because this would be ED. So to make sure you're going this way, you have to say EFD. So the measure of EFD minus the measure of ED. Like that. And that is your, that's how you would solve for the measure of angle A for all of these. Right? Again, just to recap, you take the bigger part that's in between these two lines minus the smaller part, and then you take half of whatever that answer is. Right? So let me give you a couple practice problems here. Let me erase this real quick. So here we have, okay, I apologize. That time my camera had run out of battery, so I had to stop and charge it. But now we have 3 more examples, and then we're done with chapter 10. So if we have a circle, and then we have 2 secant lines like this. Like this here. And I tell you that this is X, well, let me get the orange pen. That this is X degrees. That this is 76 degrees. And this is 178 degrees, like that. And I tell you to solve for X, right? Well, first we have to identify our 2 arcs. We have this arc and this arc inside of our red lines. And this is our larger arc. So what we do is X equals half of our larger arc, 178, minus our smaller arc, 76, like that. And then from there, if you solve that, I mean, you all know how to solve an equation. You get X equals 51 degrees, like that. And that is your answer here for problem number 1. We have 2 more. So if we draw our circle, so many circles, and we have a line like this, and a line like this, are 2 secant lines, and I tell you that this is 35 degrees. This is X degrees, and this is 100 degrees. like that. And I say solve for x. Well, here, if we were to solve for 35, you would set this up as 35 equals 1/2 of our bigger arc, 100, minus our smaller arc, x, like that. And now if you solve this, you work it down, you multiply by 2, 70, you subtract this, negative 30, you divide out the negative 1, you get 30. So you get 30 equals x when you solve it, like that. And that's just your answer. You get x equals 30 degrees. And I have one more for you. 2 tangents this time. And now we're going to draw, that's right, a circle like that with 2 tangent lines here and here, like this. And I tell you that this is 6x minus 111 degrees, and that this is 125 degrees. Oh, wrong thing. This is 125 degrees, and I want you to solve for x. So if you pause it, try to work it out. Okay, well, first we need to solve for this big arc right here that takes up the rest of the circle, right? Well, if we know a circle is worth 2 pi or 360, then we know that it should just be 360 minus 125. 360 minus 125 is 235. So we know that this big arc is 235 degrees. And if you check that, you add those together, you get 360. So from there, we can set this up again just to solve for this here. So we know that 6x minus 111 equals 1/2 of our bigger arc, 235, minus our smaller arc, 125, like that. Well, if we simplify here a bit, 235 minus 125 is 100, right? 110. Half of 110. Oh, shoot, sorry. Half of 110 equals 55. So you get 55, like that. Now, if we add this over, add 111 to 55. Oh, shoot. I'm stupid. I apologize. But we're not too far along. This should just be normal 11, not 111. In my diagram that I drew, the parenthesis wasn't curvy enough, and I thought it was another 1, but just 11. So I apologize if you paused and got it wrong. I'm sure you were right, but it should just be normal 11, like that. And then from there, if we add 11, we get 6x equals 66, and x equals 11, like that. And that's your answer. X equals 11. And if you wanted to plug that in, you get 60. You get this entire angle here is worth 55. But that's it for chapter 10. Thankfully, we're done with that. I put chapter 10 off for 3 days because I knew it was going to be this. But onto chapter 11, and in chapter 11, well, first of all, you make it back up to the, oh shoot, you make it back to the top of the book again. I don't know if you can see that. But we're going to be talking about polygons, regular polygons, and the incircle, circumcircle, radius, and the apothegm, which are all really important. I'm sure you haven't heard of yet, but on to chapter 11.